C'est bien. Alors, oui, moi, je suis d'accord. Bon travail. Tout le monde là? Du coup, on peut commencer. Oui, on attend que le niveau vienne. Un petit peu d'électricité, mais pas bien le chèque. Oui, on va pas. Qu'est-ce que c'est que les paradations? Okay. The solution. Everybody can hear from the Zoom. C'est pas problème. Voilà. Peut-être prendre the sound from here.
Alors, essayez de voir. Hello, professor. Can you hear me? Okay.
Is it okay for anyone? Do you hear me? T'as augmenté quand même. Vous m'entendez? Bon, c'est bien alors. C'est bien? Et là, on y va. So, hello everybody. So we are here together to evaluate the work, the field work of Sheikh Shah Mohammad Motiur Rahman on different denoising of scanning electron microscopy images for three-dimensional reconstruction. I am going to present the meeting. So, as usual, we will in a video conference from University of Lyon, and we have Denfese today from the University of Strasbourg. As examinators, we have Sheikh Shah from the University and Olivier Aberlé, une vidéoconférence from the University. As coordinators, we have two télé from the University of Santé and and myself, I am associate professor at the University of Lorraine. So you have opportunity for you. Yeah.
Shah Mohammad Motiur and I'm doing electron microscopy images for three-dimensional reconstruction of microstructures. I would like to start with the thanks to the members for being here today to evaluate my presentation. I will discuss about the overview of research domain, research problem, objectives, and proposed methodology, results, and key findings. I will conclude with the summary, contributions, and the future work. Scanning electron microscopy is a very powerful technique for imaging and analyzing the surface of nano-molecule surface of the particles. It is widely used in various fields, mostly in material science as well as in industrial applications. SEM may have different environmental configurations. In our research, we focus on scanning speed or dwell time. Dwell time is the time for an electron beam to stay focused per pixel during acquisition. Based on the dwell time or scanning speed, the performance of ACM may vary. For example, ACM can produce high-quality images with slower scanning speed. But it takes a lot of time. Sometimes it can destroy the sample. So it is feasible for some industrial applications. On the other hand, when the scanning speed is faster, the ACM can protect the samples, but it requires, but it introduces an uncertainty. Already, the question is arising in the literature that the noises in the ACM images are not all Gaussian. And it may be feasible for some industrial applications. That's why this is our target area, and we will work with targeting the faster scanning speeds because we want to protect the samples. And of course, with higher quality. quality. So from the introduction and the problem statement, we can see that it is very important to perform denoising techniques to remove the noise from SEM images. But in our case, we have those 3D reconstructions. So denoising technique should the technique will not rely on the blind assumption in the literature what we see. We are focusing on the latest trend of applying deep learning techniques rather than conventional techniques. From the beginning of plan to perform the research, we started with the existing techniques, the state-of-art analysis and benchmarking. Now, after that, we did 3D reconstruction. As a part of state-of-art techniques, we studied classical filtering techniques as well as transform techniques. But we focus on the deep learning techniques because those are the recent trends. In fact, in deep learning techniques may have multiple categories based on database and based on the architecture design. So based on database, it can be supervised where data is labeled, can be unsupervised where data is no label. It can be semi-supervised with a mix of label and unlabeled data. It can be supervised where the label will be generated by the network user. And the transfer learning, it can be another type. The transfer learning has a knowledge, pre-trained knowledge on other domains rather than where it is being used. So based on architectural design, it can be convolutional neural network, transformer models, it can be generative adversarial network, and it can be denoising probability model in case it is possible to combine. Okay, convolutional neural network actually applies the convolutional layer to detect the pattern like S or textures. Whereas the vision transformer, the transformer models, they split the images into multiple pages and apply self-attention mechanism. The generative model have two networks. One is generator and another is disconnector. So both competing each other and trying to generate more realistic images. Diffusion model or probabilistic model, they generate the data by adding and removing noise, and it is widely used to generate high quality numbers. As already discussed, that hybrid techniques is the mixed approach. It is used to to utilize the strength of multiple networks to solve complex tasks. So, before going to the benchmarking of state-of-art techniques, I want to start with some preliminary information how we did the benchmark. We collected a few samples from our data for SEM based on multiple dwell times. So one sample per dwell times. And as we see that, as we mentioned already, that the slower scan speed can produce high quality. So scan speed A in this case is the printer. We use pre-trained state-of-art techniques so that we can reduce the time and resource to retrain again the network. And we perform all the experiments on the major center GPU server provided by the university. We experimented with our 19 techniques. And based on the fixed signal noise ratio and structural similarity index measure, we selected 6 as a high scorer. Still, we can see that the score is not that much high. So, we interested to check visual what the result those techniques given visual. Visually here, we can see that out of 3, the first 3 techniques start to start is providing better result visually, but Cell-to-cell technique is a self-supervised technique, and it generates its own level. So it takes a lot of time. For example, in our case, for one single image, it takes almost 1 day, 19 hours to produce the results. So we chose BS again and post again because usually those are also giving a good result. Here you can see that Stonet is providing visually good results, while others have some blurry problem and they are changing the colors that they use. So they're changing the colors that they from the color. So far, we selected from the state of art, BS again, Stoner, and Bosner. We want to see some critical details of the denoising results. In some critical details, it is clear that the BSR GAN have oversmoothing issues. It changing, it removing some details. So at this part, we select both GAN and disconnect the winner so far from the table. So let's check the similarities between the weakness network. So both net and SCONET both are hybrid networks, but they use different network, combination of different networks. For example, both net use combination of GAN and CN, whereas vision and CN. We notice here one very important thing is that the both employ different noise modeling synthesizing techniques during training. So far we found from the state of art techniques that the hybrid techniques, PostNet and DiscoNet is often better. But what about the 3D reconstruction? Which was our concern that our results further will be used for 3D reconstruction. To assess the 3D reconstruction capacity, it's very important to check the key points. It's very important to check the key points in the denoised results. It is possible by applying key points matching and detection techniques, which will allow us to match the features and detect the geometric consistency of each point between the denoised results and the printer. For our case, we use accuracy detection to detect the key points. We found that SCONET is providing maximum key points in the denoised version of image. So for based on the key points, now we determine that SCONET in our case is the winner. Okay, so in summary from the scale analysis, we found that hybrid technique, especially a combination of vision transformer and CNN, SCONET outperformed. We say that, of course, SCONET is a supervised technique, so we determine that supervised technique is performing better. And we see that fixed signal noise ratio and structural signal index measure alone cannot assess the foundation of the evaluation matrix. So we propose that to consider the visual assessment also as an evaluation matrix for assessing the scanning method. In fact, we propose to consider the key point detection so that in this case, if we need the 3D reconstructions, so we can have good assessment considering each techniques like PSNR, not only just PSNR, SSN, but also visual and equivalence detection. As we already see that the top two winners have a different approach of synthesizing the data set, like making more practical data. So we found this one as our key. So let's start the contribution from the next slide. So I would like to start with noise style classification, analysis, and estimation. Initially, I started with the traditional machine learning techniques with new functions, because based on the noise type, there is some differential assumption that we can be Gaussian or it can be Poisson. So based on these assumptions, we initially targeted the traditional machine learning techniques, which are known as good performance in terms of classification of tabular data, but we have imaged them aside. So we prefer here the combination of optical image and the SLM image to have more sample as a set from state of art from online which is available, and we artificially added noise from those images. We extract the row that is so that we represent the row of the table for the measuration of the. For normalization, we perform index scalar and derivative. Finally, we train multiple traditional machine learning techniques, including the classical and also. For example, decision tree, uh, nearest neighbor sum of vector recognition, random forest, gradient boosting, string gradient boosting, in fact, stacking of multiple things. Finally, we come here and we better. So, as part of the evaluation, we calculated the precision and the accuracy calculated from the computer. And we found that ensemble techniques is performing better, more especially the stack generalization. It is ensemble technique, and it is a multi-layer approach. Once upon a time, it was known as a super runner. It has multiple layers. In first layer, there is metal runner, and the final layer, there is final predictor. So as a metal, we use random forest, decision tree, and gradient boost. And here, as a final predictor, we use exchange gradient boost. Unfortunately, with the sample we collected from Tableau, it doesn't work. And we have very limited samples. That's why we didn't explain the results here. The sample content. So from these experiments, from the initial experiments, we came up with a decision that maybe traditional machine learning techniques will not work with our case. Or it can be problem with the assumptions in the literature about the noise stack. So we felt to perform noise analysis of ACN analysis, ACN images, and to further investigate the deep learning techniques. Traditional machine learning we didn't find working well, so we decided to go with noise analysis and finally trying to investigate the deep learning models where the noise. So I start with the noise analysis of prior information for denoising techniques. We proposed a two-step approach to extract the region of interest from the sample so that the region of interest will be a flat area without any additional texture, like to have a global analysis. So in first step, we take an input and we split the images into multiple tile size, in multiple tiles. We selected tile size. And we keep track of the mean pixel values of each tile. And both as an input we use in the second part. Why we keep track of the mean pixel values? Because we were interested to identify the higher density pixel. Because we all know that higher density pixel can explain more details about the information. In our case, we perform mean shifting to move forward from mean to max, from mean to max, and we found 15 values as a candidate to this region of interest. From 15 values, finally, we did a manual analysis to be sure that there will be no additional texture in the selected RY. And this is one example of vision interest, and you see that is completely independent before any additional features. We perform this technique to validate with 4 samples per SEM. So we use 2 SEM and total 8 samples. We evaluate the technique statistically as well as uh, fitting the probability distribution function of the different noise distribution. Statistically, we check only the distribution of the RY, whether it's Gaussian or not. And we found that yes, that's true. It was in the definition the question was arising, but it's true that it's not always Gaussian. After a certain time, change the time. After a certain time, we change the type from Gaussian to something else. So the question is, what is that type? So we performed filter test, fitting with different probability functions, and we found that after a certain time, the Gaussian changed the gamma distribution. In fact, we tested with 2 SEM, that one and the second one is the right side. And there is the changes with T square, and T square is a spatial category of gamma distribution. So in general, we decided that it's transforming gamma distribution from Gaussian to gamma after a certain time. So the key findings is from this noise analysis is that after a certain time of real time, the noise distribution is changing the type from Gaussian to gamma. The limitation of this proposal is we tested with only samples from 2 SEM, but this is most important that the 2 SEM have the consistency with the results, similar kind of results in both. Based on the findings in the noise analysis, the Gaussian and gamma, now we interested to implement the deep learning approach to automate the noise information. So for automating the noise information, we need a data set based on the findings what we find the Gaussian and gamma. We prepare a data set from a publicly available data set of SEM. Those are key targets. So artificially we added noise, and for Gaussian, sigma is the level, but for gamma there is a true shape and scale. Just both accounted and level. And we prepare 2 data sets for Gaussian and for gamma, and we stored accordingly the type and the level. Because we were interested to not only just to automate the type but also the level. Finally, these are the samples, the clean samples, what we use from the literature. And after getting the Gaussian noise, based on different sigma value, that is based on different levels, prepare a Gaussian data set of Gaussian samples, similarly the gamma and with a different scale and shape value. So to automate, here we see that there is a two process. One is the noise type classification, another is noise level distribution. So to automate this process, we propose 2 methods. One is classification, another is regression. So classification can classify whether it's Gaussian or gamma, and regression can predict that value. So in classification, we experimented multiple techniques to identify the better one, which one is well fitted in our case. Before going to the classification learning phase, we performed a feature engineering phase. So in feature engineering phase, for simple neural network, we use pre-trained techniques for extracting the feature. For example, the pre-trained techniques like VUV, ResNet, or EfficientNet, they have previous knowledge on different images. So we give our images to them, the features one understand from that. Their features we use as an input of our simple neural network. And for other techniques, we train the transfer learning, vision transformer. For other techniques, we use the user condition as a part of the training. Then we compare the results and we predict them. So as a result, we found in for gamma, that the accuracy is not good. So we found that for gamma, there is still problem. We identified that the problem happened because gamma have two levels, like shape and scale, and we found in the literature that there is a problem with shape value because after a certain time, shape after a certain value of shape, gamma distribution changed the criteria. That's why we shape value and we count scale as a parameter or level. And we found that gamma noise classification becomes increased. Similarly, we did for regression. And in regression, we see the for the estimating the Gaussian noise is good, performing good results, but the same problem with the gamma. And we did the same configuration what we did in the classification that fixing the shape value and predicting counting scale as a level. We did the same. We see that the result is good, but there is problem. There is a huge here. So finally, we come up with conclusion that the proposed technique is good for estimating Gaussian noise, but not for gamma noise. And for estimating Gaussian noise, Westnet and VGZ as a feature extractor is giving more meaningful features to the classifier. And we identified that gamma noise have performance problem. It is somehow connected to the shape and scale. Because the higher shape transform the gamma noise. So it is clear that it is very difficult to identify the noise information if it's not Gaussian. So we propose to consider blind image, like without knowing the prior information about noise, then perform it. Based on this consideration, we consider that the technique is performing better. So we consider the synthesizing in as a network and finally during synthesizing the data set, we have an assumption of a set of noise models. So we follow the concept of set theory. We take, for example, n number of noise models as a set, and we calculated that combination based on the power set concept. In the power set concept, it can be 2 power n, but it's including the n. In our case, we don't want efficient because it has no noise model. So for our case, the number of subset will be 2 power n minus 1. So more practically, in our case, we use 5 noise models: Gaussian, gamma, speckle, and Poisson. Based on this 5 model, we calculate the combination of noise models. So in our case, 2 power 5 minus 1, 35 initial subsets. 31 initial subsets. And this 31 initial subset means 31 virtually data set. I mean, the system will create 31 data set based on each combination. And finally, we trained that linear network. We use the ESCONET network, which was performing data information. ESCONET is working in the top of the unit architecture. So it's using unit architecture as backbone, and it has 4 skulls, multiple blocks here, but it integrates each block. It integrates or it introduces a new block, is swine conf block. It is a combination of swine transformer and usual convolutional network reusable conversion block. Both combinedly working combinations, splitting and truncating, and finally making connections, and finally performing that. So the synthesized data set was trained in was used to train the denoiser network. And finally, we used the ranker because we have 13 data set. That means we have 13 denoiser based on the training. Now, there is a module called ranker. Ranker is taking the denoiser, the list of stored trained denoiser, and taking the actual sample, noisy sample, and it is performing denoising iteratively and comparing with the clean target and calculating PSNR and SSIM to rank the winner one. So this is how it's trying to get more closer combination to the sample. So this is the architectural diagram of the proposed technique. We call it M ranker because we are ranking the noise model combination. So here is the list of noise model. We are making the combination except the empty set. And how many combinations that synthesizer is generating that much data set and training. And that must 2 power n minus 1 times number of linear that is trained that is can be the output to the ranker. And then ranker is performing denoising with the real resonance characteristics and comparatively is trying to adapt which noise model is more closer to the real sample. So as the output we are finding as a combination of noise model which is being adapted by the ranker and the noise are trained on that combination. So as the output we have two. I mentioned these techniques, our proposal in the same center provided by the university, and we use Python, PyTorch, and OpenCV. For training our proposal, our techniques, we used 500 samples from the literature, which is already available, and we made the selected 500 available in during training, we splitting each image in 10 page size. So ultimately, 500 samples is producing 5,000 samples before going to the training during the synthesis. And we perform testing with samples collected from him. And we were limited to use batch size 8 because we were facing issues in out of memory in the server after 3 iterations, more than that batch size. We tested multiple echo to check whether there is any impact on performance based on the echo number of echo. We see that the completion time is very high. So as a result, we started with eliminating the combination, noise combination, because we have 31. So we started with eliminating the number of combinations. We eliminated 22 combinations visually. Why? Because in the state of art, we see that visually makes sense rather than PSNR. And we eliminated total 32 combinations visually. Finally, we found the 9 visually good. And then we performed another assessment based on PSNR and SSIM. We selected the top 4 for experimenting further. So we experimented with that 4 combination with 200 echo, and we found that the performance based on the number of echo, it doesn't change that much. But it needs more than 8 days time, experimental time. So, in fact, for ISCONET, the network we use, we found that in their paper, in their work, they use more than 200,000 inputs for getting their results, and for our case, we reach by 22. So we think that comparatively, uh, our proposal in terms of resource and time efficiency is performing better. But what about the 3D reconstruction? We have now 4 combination is performing better. So which one is really good in terms of the real application? So we focus on the 3D reconstruction capacity of each step. So we find that for small scan speed, the combination of speckle and pepper solve is providing maximum key points, whereas medium speed is providing speckle alone providing good key points. But for Foster, which was our target, Foster scan speed, the combination of speckle and Poisson was providing maximum key points in the results. In fact, on an average, if we see that the combination of speckle and Poisson, it had a very good balance for each scan speed. Now, we found that the combination of speckle Poisson is providing better results, but we want to see visual, check the results visual. And you can see that the denoise results is quite good. We zoom the details to check whether there is any other issues or not, and to look into the details of the results of this process. So it provides almost clean like output. So whenever I present my presentation of my work throughout the research, I always use the pollen grain sample title from Denfese. So I was asked this question of that is there any more samples or not. So I had no answers that time, but now yes, I answers, and we found few samples from Denfese, and we tested with few samples of dust and some samples of hole. You can see that the results of the denoise based on the according to each scanning speed is better. It's providing almost good results. So what we are telling is as an adaptive blind denoising. This is a question. So I would like to start with the blind denoising. Blind denoising is performing denoising without having prior knowledge or having prior information about noise. And adaptive is the performing denoising by the local content of the input images. So mix of both is adaptive blind denoising. This is exactly in our case. In our case, our technique have a list of assumptions, but it has no knowledge of the input, what kind of noise in the input, and it is trying to identify, it is trying to adapt from the assumption, which assumption is more closer to the input image, the noise of the input. This is why is called adaptive and blind denoising. So as conclusion of the study and the contributions. So we proposed that in our technique, you can see that we focused on synthesizing realistic data set rather than exploring a lot of new network, because in the literature there is already outperformer network exists. So it's important to focus on how to improve or how can make a diversity of the state of our proposal. So we focus on synthesizing more realistic data set rather than experimenting new networks. In fact, in noise analysis and noise estimation automation, we see that there is unpredictable nature of noise in the SEM images, and that's why we proposed blind denoising to perform denoising, propose denoising of SCM images. In fact, we open a new dimension in the blind denoising areas, that adaptness. So to adapting based on the input. In fact, it can be a very good point that the combination of noise, like we found that mix of Poisson and speckle noise was performing better in denoising. So it was not explored before. So it also opened a new dimension to think about. Of course, we proposed that key points preservation, and we showed that is very important for 3D reconstruction. So in our case, it's throughout the research, I published one Q2 journal, one Q1 journal is under review, under second phase revision, two conference papers, and one conference and another Q1 journal submitted. So the proposed technique is possible to improve in future by improving, performing the tuning of hyperparameters of the model. For example, in fact, for the generating the synthesizing noise, the proportion and the speckle, we didn't try with a different combination of the level sigma value. We just try with sigma value 35 to keep it fixed. Why we didn't try? Because you see the experimental time was it was taking a lot of time, and it is possible to use this technique in different domains rather than the SEM. So that we can see that the proposed framework is uniformly worked on. And integrating the explainability inside the proposed techniques can be a good point to make transparent to make more transparent of the proposed technique. In fact, the adaptive concept can be applied in the denoising diffusion probabilistic model on the noise sampler module, because on that technique as well, there is a blind assumption of Gaussian. So already they use a Gaussian, but there is a changes in the literature. I found someone use gamma. So it can be a good idea to implement the adaptness, so that each time based on the sample, based on the input, it will adapt the noise. In fact, the proposed of making speckle and Poisson noise in the SCM images, it can be a good idea to validate it by analyzing SCM images, because we validate when we do analysis, we do analysis with each single images, single noise type, not the combination. So it can be a good idea that to check the combination whether it exists in the SCM image. In fact, in the output we can see the key points. It's not providing all the key points. It's not preserving all the key points what is exist in the target. So it can be a good idea to apply reconstruction, so that after denoising, so that we can reconstruct the missing key points. And that's all today. Thanks for your time and attention. And now I'm ready to have questions.
Okay, thank you for this presentation. Now we are going to go to the questions. And we are going to begin with Ricoeur. Beginning with Stéphane Frétia, who is in the video conference. Do you hear us? Hello? Ah, yes.
Yes.
Let's go properties of the signal. Um, so I think that the work is a sound contribution to the possibility of using deep learning of techniques for generating solutions for those problems. And I thank you for making this possible for other people to appreciate and maybe to take as a starting point for their research. So thanks a lot for this contribution. Your manuscript was very interesting as well because it showcases a lot of interesting contributions based on the very good ideas about how system works. So, as a statistician, I think there are lots of interesting points made, also about the systems that you were dealing with. And you have did you see in the exploration phase of the thesis when you were reading the literature about those models, did you see say a statistical model of the whole system that explains the presence of different types of noise?
So the statistical, I think, if I'm not mistaken, you mean the statistical method?
The statistical model.
Model.
Yeah, that describes why certain types of noise are present. Is it linear? Is it linear? The relationship.
Okay. Normally, from the state.
To be looking for this background before we can assess the relevance of the learning approach for this problem.
Okay. Normally, for statistical method, I didn't go into details on that, but in the ACL, normally it is in some papers they discuss about the produce of noise in capability embedded in steady state and found that in steady state it stays the noise is providing Poisson noise. And in fact, the combination, if there is multiple sequential event of Poisson noise, it transfers to gamma. So when we found the analysis results is that gamma is Gaussian is transforming to gamma, so we were able to see that something relevant. But it doesn't work in terms of deep learning based techniques. And more specifically, we were more focused on the deep learning based techniques.
Okay, thanks. So I'm really interested in maybe drawing to this modeling a bit further. And if you have nice references about this, it would be interesting. Good. So, I mean, I was wondering if statistical methods for addressing learning from like variation methods. Have you heard of this kind of approach? Or
I think no. Yeah, because from the beginning it was we were focusing on the deep learning techniques, but in the state of ours, what I was looking for that like the evaluation of the techniques, how it comes from the filtering techniques to transform techniques, then multi-layer perceptron, then deep learning. So I was focusing on that. So more, I mean, more focusing on deep learning than statistical methods.
okay, but the deep learning approach may allow you to capture the say the signal. You have this noise of varies like what's normal version. So this can also be used in AI framework or more specific framework, which can give you the guarantees about the specific performance of your pipeline. And I mean, this is not incompatible with the statistical model.
Yes, it can be a good idea. Yes.
And so the way you assess that your what the quality of the result is also, I think, the issue in this project. And you remark that it's also to be included the results. How would you describe the limitations of how the say how the performance, the way you describe that, can suffer from some weakness?
Is I think that like visual assessment why I propose. In fact, for me, fixed signal noise ratio similarity index is not working well because I'm sure it has details. And scanning electron microscopy, when we collected the clean tablet, it has a lot of details. But after denoising, I'm sure that when we compare, we are not getting the same similar structure or similar noise or similar distribution of this pixel in the denoise results and the peak target. So there is still a problem. I mean, that's why finally I said that it can be a good idea to perform the reconstruction as well, because deep learning techniques may remove some details. That's why the other assessment metrics is not giving better. That's why I say the visual assessment is also important to have at least to make a decision, because it is very difficult to make decisions based on the signal issue and structure of similar.
Okay, thank you. I was wondering how fine grained can be the approach of measuring the error. Like, there's maybe how much is even some people focus on how bad the error is, and the error may not be problematic in other areas. Okay, so how do you take that into account?
I think I was proposing to count key point detection as well. So it can be a good idea to track the key points of the denoised version according to the clean images, so that we can. I believe that by using key points detection, the evaluation metrics, it can be possible to minimize the errors, and in fact, it can. I mean, based on the some threshold point of key points, we can perform denoising or reconstruction. So it can be a pipeline to improve the quality of images again and again to reduce the errors. And I'm sure that there is errors because there are some clean, some very small details like some blend points or small blend points. Those are getting removed in the image version. In fact, in the literature, when we compare with the results with key point matching, we see that there is some mismatch in the key points as well. So I believe that key points tracking can be a good idea to minimize the errors in the system.
Okay, thank you. So a lot of interesting questions still to be addressed. I'm sure your work is a foundation part of this path with having something to achieve actually more. This is very interesting. So I was having more technical questions about deep learning and the world we connect. So you face the issue of observing overfitting sometimes, or how do you manage the complexity of your network in order to make sure that there is no kind of overfitting present in your
Yes, this is also the one of the reason that for the moment we didn't test it with the overfitting. To be honest, we were focusing on the results from the beginning. But for previous experiments, what we did, we applied cross validation, like for careful validation, cross validation to I mean, uh, overcome that. And in disconnect network, there is itself considering the early discovering and flex normalization. There is implement dropout rate, few things implemented to tackle the overfitting issues. So that's why we were focusing on those features. So we didn't completely change it by ourselves. That's why we say hyperparameter tuning can be helpful for to have more accurate results in the future.
Thanks. And so there is a vast literature on hydroponics maturity. So do you think that exploring this literature could give you faster algorithms?
Yes, I believe because the number of layers, the complexities inside the network, it can be reduced, and sometimes there is some, for example, when you start with the learning rate, learning optimizer, Adam learning optimizer used, but it can be interesting to check multiple, I mean, optimizers as well as multiple learning rate and some other, number of layers, minimizing the number of layers. It can help to have, I think, good performance by tuning parameters of the network. So as we use the network directly from the state of art, so we can perform the optimizer. This why I think it can be a good idea to perform focus on the tuning.
I think again, this is also key to getting good performance with people.
Yes, in fact, we didn't perform a lot of experiments because of the time. Because when we experiment, we found the server it is giving output maybe after 7 days, after 5 days, after 8 days. So if we had intention to experiment more. In fact, if you see I already mentioned that in fact the sigma value we fixed it. We didn't try with multiple values because the experimenting was taking a lot of time. We were trying to have a better resource. So far we had the resource we used.
Thank you. I'm also very interested in discussing with you the possible future works you were mentioning. And I'm very excited by the line of research related to XAI. So can you tell me more about your plans in this direction of research?
Yes, the explainability actually, like, look, you give you ask a question about our fitting, those questions, hyperparameter tuning can help or not. So what we are doing now is a black box. So what is inside, we are not focusing on the processing step. So explainability, there is a great library. They use explainability of deep learning networks. What they do normally they track each step of learning the network and tracking the the most important part from the data set from where the model is learning. So identifying that it will be more transparent to the experts. They can see that not only black box, I can see that how the model is learning. And I can interpret that, okay, this is focusing on these 4 features and this is not relevant. It is irrelevant. So it can make a bias or it can make a problem in our fitting. So those can be easily identifiable by expert if we can apply the explainability. So explainability is kinds of making transformation of making transparency of the model.
Okay. Some.
Yeah, I said explainability. I said explainability is something like making transparency of the learning process of the model.
And so, any of the techniques for performing sort of explaining step. So, which of these techniques?
There is one I was planning. In fact, I implemented just to identify it's called gradient tracking, like gradient can. So the techniques is well studied in terms of this conservation. So I check the features of the images. Not only I check only the one feature, which features were more giving more meaningful information or more bias during the image, not in the training because training takes a lot of time. So it's kind of great gradient. I think I forgot the exact name, but it's a gradient can.
Okay, I know this.
Yeah.
Okay, very good. Okay, and so we have time for the last question.
Yes, yes.
I was also interested in the way you were trying to use the DDPM. So can you tell us more about this?
Yes, because in DDPM, using diffusion for holistic model, we see that in noise sampler, normally they use, Gaussian noise by randomly adding Gaussian noise and removing them. But the problem is we were talking about the noise type. So it is possible to implement the adaptness, like make an assumption and perform the denoising, training and denoising, and then identify the most closer one to the input. So the adapters module can be implemented inside the noise schedule on the DVD. So this was I was thinking that in fact I implemented on there. It's not shown here because it's done in the server. The idea is just making variable, not fixed with the noise type, like Gaussian. No blind assumption. Adapting based on the input. So we will do assumption and we will adapt from the input. So this module can be included in the noise sampling process of the DVD.
Okay. Okay, I think this is okay. Thank you.
Thank you very much. So now we are going to hear the second reviewer, everybody.
Okay, thank you for this clear presentation. The reflection for your speech is to more on that, so I will make some choice on it. I will begin by the last question. For me, for the process, um, there is one fundamental problem which is related to the type of noise. Because this given process is based on an additive process. You add questionnaires. It can be another noise, but it's additive. And the end of your that shows that the noise that is problematic, not the virtual noise, but the noise that is interesting on problematic the SEM images is not. So,
but the thing is that in fact, during synthesizing our data set, we perform additive process. We did the noise generation separately. We added with the images with editing process, and we counted the appropriate based on the limit, is the limit we want. So this is the combination of mixing the multiplicity, noise, and noise. Those are we are talking separately. And after, when we are in the network, we are adding it, following editing. Multiple noise is there. We mix multiple noise together, and here is sample. So image. So here we are talking with editing process. So we are adding with editing process together, noise together.
but if you add spectral noise and spectral noise, spectral noise, both of them are independent. So you will detect fundamental noise. Is it possible by diffusion to simulate or to denoise the noise?
Yes. But the mixing is possible this way, but not single noise. Because single noise.
You have a paper based on saying that it's possible to generate to simulate this kind of.
No, it was just a proposal for future so that we can test on that. So we can try on that.
Okay. Come back from the vocabulary and line. Because at first, when I read, I didn't understand what you mean. So I know I think I understood. You mean that you are blind to noise type.
Noise information.
Noise type.
Yes.
But what you propose is a denoising effect. And for this effect, not only the part of identifying the type of noise, you use clear image to a noisy image, so it's not blind for the denoising whole process. It's
Normally, so far I understood that fusion is okay. It's trained on other domain. Is a pre-trained techniques, but training with a fusion plan. But in our case, we don't use the pre-trained techniques. We completely just the network and we train on our data set. Not like we have only few samples, we train on few samples. We prepare a list of data set and we train.
clear. If you use a noisy image, don't say it's blind. You have to use a clear image on the noise. So you give the noise. You for a denoising step, just like you give the target.
This is during the training. But if you see in terms of the performing denoising, on that part we are using random targets, and that's why we didn't click with that. It's adaptive line denoising. It's adapting. It has based on it has assumption. Based on assumption, it is comparing that aspect. But it is adapting based on the the target, the input. This is why we say this. Yeah, I understood. I'm sure that it's not completely 100% blind. That's why we say it's relatively blind, and it's not 100% clear.
Yeah, that's why I say I understand more because you are blind on the noise type.
Yeah.
I don't. Another point for the fact that you can test several values. It's quite that. You work on the HPC.
That HPC was done.
HPC is high performance sensor. So for the sensor, it's middle size HPC. What would you maybe you do to send the response in parallel?
Okay, because initially I was not performing parallel. When I got to know that it's possible to perform parallel, I was almost finishing in my thesis, so I didn't go with the. In fact, the code was not comfortable with the. It was sequential.
Okay, you did a previous learn. I will change the it's very important.
I used I submitted a job and I found out 4 hours after 3, 4, 5 days time, but in terms of GPU uses, I didn't use parallel GPU. This was a problem, but I understood from the end of my thesis talking with someone responsible for medicine in Denfese, I understood that it is possible to submit parallel. If I ask them, they will give me such kind of permission. I was trying, it was not running automatically.
So for the beginning of your introduction, you have to be clear for because you have two programs. Classification program, the noise on the denoising program. It's not just and when you speak about service provider, you have the pastor. One of the time is like the loss, but it's not like that. And the time for denoising. And for this same problem for this for classification of different models. It's possible, but it's quite tricky. It's hard, denoising. So it's here, yes, in this aspect. But you say it's very difficult. The better result. It's obvious.
It is based on the state of our experiments.
Yes, when it's supervised, it's here.
Yeah, that's true.
Okay, I'll go back to the oh, yeah, I have a main question that I think trying to identify the good kind of noise that you reactualize it for the machine learning techniques. So, we are just, why not? Maybe it works. Maybe it works. It's so I was a little confused by the fact that you have values for the parameter for some noise in chapter 3 and after in the last chapter. Actually, it's the same between 0 and 1. Wow. Is it the same kind of noise? Difficult to. So maybe it'd be a good idea to normalize it, even for the next friends to understand what is useful, visible. In the regression, we evaluate with MSC, mixed error, and also with root MSC. And after, we give the best for both. But when you make a root square, it's increasing. So it will give the same rank as a mixed error. So just have to maybe be careful. You have two eyes, but it's always a bit of science. And then I was wondering for the log error you use, can you tell me what you use the whole thing for log
It's
error?
multiple errors to check what we use to check in which assessment criteria is being behavior. Not intentionally just to check specific something or getting something from the literature. We are focusing on multiple assessment techniques because from the actually state of art, when we analyze the denoising, we see that fixed number ratio and other techniques was not being used for other experiments that was motivated to explore different information.
For me, log is like you have kind of different of logic with Z, 100, 100, and the cubic scale to be basically compared. But here, when you use this log, as it is not so scale, the difference are very because the log is different. I'm not sure it can be used. Okay. Well, in the same kind of question, you have certified combination. Something like English, something like this. People will use that. Was it possible to reduce because some combination are maybe the same, like by the theoretical properties, always the question, or like the gamma plus the I think.
Okay. I didn't consider that.
Yes, you could.
Yes. Mix of multiple can give similar properties with some other.
Yes. And the combination is made by addition. That's what you say. Because in the manuscript, it's very difficult. I didn't find how this combination. It's okay. But the aspect of reconstruction is interesting. I was wondering when you say, okay, you can reconstruct, so you will use several images. To reconstruct, you need several images. And maybe the fact that you use these several images can minimize the resulting reconstructive quality. The volume reconstruction will use information from several images. So it will make like an estimation of the average value.
Yes.
So will it be necessary to denoise the image?
I think yes, denoise is necessary because taking rid of some additional information. Reconstruction and have a chance to reproduce the model, reconstruct the model.
And on this point, the mention that the point of interest is it's like end user goal. So,
Thank you very much. We can see Olivier Gagarret, who is in the video. Hi. Very good. And you
Oui.
Voilà.
Olivier, tu nous entends?
Ah, voilà. Ok.
Vous entendez, c'est très haché. Peut-être pas moi qui prends le micro.
You have to get closer to the micro. Because it does not have a very good.
Ah,
You can go.
Okay, yeah. Okay, thank you. Hear me?
Yes.
Okay, thanks. Okay, thanks for the presentation. I think it was nice. You made a good effort in presenting results which are not always easy to present. First, I would like also to thank Sheikh Shah Mohammad Motiur and Sheikh with you. I'm very sorry for that, but at least we have the video now. Thanks for the manuscript. I appreciate it after you sent it well on time. It was nice to read. It has been said by the viewers, but I can try to emphasize that it's nicely written. I am not a specialist of this learning method. I have learned many things. So, reconstructures, you have a huge goal, and you achieve most of the results, and it's opening some possibilities for the future. So I think it was a very interesting work. It's a scientifically found, which is proof that something happened. We are here to follow it up. So I come now to the defense itself. So it's, to me, it reflects well the manuscript. What I appreciate is benchmarking algorithm is quite tedious and it's often a thankless task. But it's a very important point in the development process of the scientific method. You did the job, I would say, and you have latest results. They have been published in conferences and in papers, as you have mentioned at the end. There are new papers to be published, so that's also very, I would say, encouraging for the future. From my background, being more an experimentalist, I will focus a little bit more on this. There have been already many questions on the image processing part. But first, a general question, I would say. From what you have learned, testing, benchmarking all these various algorithms, so it's a point of view, so not easy to contradict me by wrong, but do you think it's worth still developing yet another algorithm? Or from what you have found in the box, is it okay for the task, the future task of processing this, for example, this foreign electron microscopy images?
Yes, I say the similar thing that it is like focusing improving performance or making a diverse implementation of state of art techniques can be a good idea rather than implementing new techniques. So this is the one actually I learned multiple techniques just uh, changing the few parameters, few blocks, few layers, which can be a few, for example, concepts like in hybrid techniques we see that can be combination of CNN, and then can be combination of vision transformer and CNN itself. Yes, experimenting or proposing new networks, I think existing techniques from the state of art techniques I found that they are really, really good. In fact, those techniques are not focusing on SC, but those techniques were able to work on the samples of scanning techniques. So it's very important rather than proposing new technique, but focusing implementing a module or implementing a function to improve the result idea from the existing technique. So this is the learning that's one.
Okay, thanks. From what I understood, so now the data set is available in the GitHub.
Yes, this data set actually is selected from one existing data set from each and we selected based on the resolution first, and then we check manually to be sure that the images are visually also good, because we are focusing on visually. As I already proposed that visual assessment is important. So based on that, we selected 500 images. There was more than 21,000 images in the data set.
Okay. So this data set is already, I would say, advertised in one of your papers?
Yes, multiple paper.
Okay. So that's important for the data set to be reused by other people.
Yeah.
Okay. Can you come back? I would like to come back to what you said. It is indeed important. First, okay, for example, slide 16. That was when you checked the denoising. Yes. Yeah. We trust the clean image. Okay, let's say. I will say that your visual assessment, if we look at the denoised image, we lose the small features which are on the surface of the polygon, the smallest feature. So, okay, I agree with you. But the problem of visual assessment is it's very user dependent, so it's very of the user. It's also very sample dependent, because on some samples it may argue that what you are suppressing are structures, or maybe not, they are not. So if you want to have this say more widely used by non-specialists, at a certain time you have to get rid of this visual assessment, which is good when you are an expert of the domain, like you. But other people, if they want to observe not foreign grain but something else, maybe they will have a different opinion. What kind of criteria could you use to, I would say, more quantitative assess quality of the people?
I think big signal line ratio and structural similarity index so far is better, but for us, I explained already that okay, this problem can be happen because after denoising some small details is getting removed. That was the problem. That's true, and that's why the standard resolution techniques was criteria of which are other details were not working properly because they were not finding the details in the denoised results. I agree with you that visual assessment will not is kind of new on us. But for visual assessment is not only just determining the quality, but also just to that visual. And as well, based on you question that what criteria can you accept? Like as I explained that, I think the key points negation technique can be a good way to use as a loss function or as a evaluation technique. This was a kind of idea from myself.
Okay. Um, I, I'm more interested in this point, especially I'm mostly working in optical microscopy. In optical microscopy, we also may have a very different type of noise, as you mentioned for electron microscopy. For example, spatial noise in holography, Poisson's noise is important when we use fluorescence microscopy, etc. If you look at other domains where we made, for example, synthetic temperature radar are very strange images where everything is more or less correlated noise. Did you also have a look at this other domain? Because um, I'm suspicious what you develop could be adapted to rather difficult. So if you say that it's not easy, but could be adapted as of interest for people in other domains. You already have a look?
No, I didn't have a look actually because that's why we say that the future work we can just with other domain to have to check the uniformness of the proposal. So we didn't just get there with other samples.
Okay. Yeah, it's an important volume in hours of work. So we imagine you can transfer the just demonstrate it.
Yes.
I'm coming back to the chapter in PhD about the noise for me was interesting, as I said, because it's always a problem when you are not in the best conditions to take images. And so my question was a bit more related to the way the electron microscope works, the way it has not your main specialty, but anyway, it's interesting. Um, you mentioned essentially a problem with the pixel dwell time. When going very fast, it's noisy, you have time, it's slow, but you get better images, and say the classical photon noise, which is very easier to deal with. Um, but I'm suspicious the various level of noise and the nature of the noise could also be linked, for example, to applications of energy.
Yes.
Did you also investigate?
No, we only investigated on the real time.
Okay.
So as I mentioned that it can have different configurations and it may depend on the configuration. But we focus on the real time performance.
In practice, of course, important, right?
Yes.
It defines the number of images you can take, etc. But I would not be surprised that these are the samples. Yeah, Mr. Like, okay, so you do not have charging effect appearing and this kind of thing. Because that's another kind of thing you may have in the electron microscopy. Okay. Then let me come back to sorry, I forgot to mention the number of the slide. That's the slide when you show the correspondence.
Correspondences.
Yeah. The number of points you find between the both images.
Yes, okay, bro. It's
Okay, yeah, here we are. So then basically I was wondering, could this not simply be a criteria you implement your algorithm? you denoise it and then you check.
No, I said it can be an idea, a good idea. Mm.
But you didn't do it yet.
No, I didn't do it.
Okay, I imagine it's not so easy too, but because that's in fact we make tool, having correspondence. So I think it should be a great, it would be a natural area, I think, uh, when you want to make a big reconstructions and this kind of things. So if this is the goal, it seems natural to try to introduce it in the algorithm.
Yes, okay.
And you have an idea on how you could introduce it?
As I said that it's possible to like kind of tracking the losses of sequence according to the linear noise.
Mhm. Okay.
Calculating the loss.
Okay. I will not go too much into I have other questions, but maybe they are technical, so I will keep them maybe for discussions with your PhD advisors. But I will then I come back to a more general question. You have learned a lot of things about image processing, technology, artificial intelligence, CNN, etc. What is your goal now? Do you have already any ideas how to implement this in future work?
Okay. These techniques actually, the idea was to working with real application implementation, just not only simulation and making results and application. So that's why normally I was trying to prepare a tool for that, but it was the results or the techniques what we proposed or what we performed is not well enough mature to make it a permanent. So, but in future I have an idea to work with this the knowledge again from this study and prepare a tool for the scanning electron microscopy, not only that with the other areas as well.
Okay. Okay. That's you work on. That's important to have the tools which you are not the sole guy able to use. And that requires effort too.
In fact, it is important to have explainability. So the future target can be a good idea to make a trust for the AI by making transparency to the expert. But how that we train just not following blindly to the black box.
Yeah, that is a point which is often mentioned about black boxes.
Yes.
Which is my last question. That's a new, rather new domain of development, so-called physics-driven artificial intelligence. So to implement the laws of physics to improve the results. You already have a look. It's widely used in optical microscopy. I don't know in electron microscopy.
So far I didn't go from there.
Okay. Okay. Anyway, then, I would like to repeat. I was very pleased reading your manuscript. It was nice hearing you today. So, Mr. President, I forward with my question. Okay, thank you very much. So now we need to go to Mr. Motiur.
First of all, I would like to thank the first visit from the and it was really interesting for me to read your manuscript. I'm not an expert of semi, so I have a pretty question. But we don't have to show another question because we have the result. First of all, as told you, I'm not an expert on cell activities, and something I was basic at the beginning of the manuscript is the description of the formation of the Scanning activities. And I think it's very important to, to understand why you have this type of flow, because it's not clear for me why you have some type of nodes or gamma nodes within the what we call the well time. But normally if this why you have this threshold to velocity of the sun and
this is what should be identified in the literature. Right? It's not always push. Then we start from we are concerned about the noise time. Then we start from the analysis. So finally, we found that after a certain time, it changed the type of the noise. So it's we focused on the real time. That's why we are. This is a very good question. I don't think so. I think that it has other influence from other environmental configuration as well. But we were collecting the same configuration with changing the real time. We checked with the real time. It can be a question to further research on that.
okay. So you a question about the goal and the question your testing. So for that we need to know drugs who have a trade-off between denoising and the I mean it should be known about some drugs.
Yes.
And this is interesting kind of strategy because this is why I my paper because okay you time for comparison and also the number of phones that are able to get. For 3D reconstruction, I'm not sure that it's really a good deal because for 3D reconstruction, what is really important for sure, this is the number of match you have to reconstruct the as best as possible. That you have to be sure also that the phones are really well localized.
Yes.
Okay, so maybe there is a trade-off between, for example, UGB and UGC. I don't know if Bootnet will be better if your detector and your phone are well localized than UHC.
Yes.
So,
This is a good comment. I didn't consider that. Yes, of course, this is a good idea. The localization of the point. So this is actually for like geometric consistency.
yes. You add some pressure in your water. So you are not sure that your phone are well localized.
We use a threshold and point of 0.75 level and match it.
Okay, so you go deeply into later, but as you mentioned in your first chapter, you have a lot of classical methods that you are not really counter.
Okay. I mean, the classical
We use the evaluation method and
deep learning.
Yes.
Yes. That's true because we are focused on the deep learning, but initially we are trying to identify the noise, how to classify with small.
Yes.
So we consider traditional machine learning, and a good idea to make a comparison because we have results in at least for Gaussian line, we have results with deep learning. So machine learning and deep learning. And for real case, for real sample, machine learning, traditional machine learning technique was not performing. That's why we didn't consider to go with that further and we will make comparison.
Yes, yeah, it is good to see finally if the support that amounts to use some classical way to do the job with the direction. Just to see the leisure of this effort in this type of project, I think.
Yeah.
Yeah, because I really checked not to blind denoising because we would suppose that it might have kind of flow. You have some motion, gamma, but in practice, I'm sure that literally the neuroengineering follows this kind of flow, or this type of flow.
Maybe because that's why I said that it can be a good idea to validate the findings before really possible statistically to check the distribution, noise distribution. Checking the combination of probability distribution function. So because we test with single probability distribution function for each noise. But we can try with if there is any mix, so what will be the probability distribution function?
Because I believe that the first two people that was two types of noise, gamma and
Correlation and person in the literature. Yes, there is spectrum, paper, and salt. Yes, I think I think it's an example. At the beginning, during the test, there was the first circle, because first circle was based on the assumption in the literature. So the assumption was the Poisson was Gaussian.
So you finally you are able to tell me that it's not the difference.
These assumptions was right that it's not. In fact, after certain value, Poisson changed to Gaussian. So it's not a Poisson. So the question was in the and in one publication in Cambridge Press, they said it can be flattened. So nothing was like for sure that it is exact. Okay. So this is why we focus on that. Noise analysis should be performed because our task was working with denoising. So normally people do blindly assumption, make assumption from the literature and perform the denoising. But when we found that there is a question and which is not solved, so we wanted to check. So we found a new thing like gamma noise. In fact, gamma noise have relation. We found a relation because every step of SEM events is providing Poisson noise, and we found that series of Poisson noise can produce gamma noise. So there was relation. So that's why we found interesting that then also maybe we can say that implementing how we implemented the gamma noise, it can be a problem on their implementation. Because in the statistical analysis, we found this gamma noise or probability distribution fitting function. But in terms of automation, gamma noise doesn't work. So that's why we try to make something not just focusing on one single noise.
Slide 47, I was super because your MSC was really important. Yes. Why could you explain why you have 26 in terms of MSC?
Mainstream, yes, because of the combination of shape and scale. We fix the shape value. Okay. So when I suppose there is a problem in that generation when we use 5 as a shape value, it's not providing multiplication of shape and scale. So it's changing the value. So it's not only focusing exactly the scale. So that's why I can assume that that's why the problem in the scale the level is during the implementation. When we do implementation, we see that this is the good one. But finally, after when we look back, there is something.
So before we go to the I will have some remarks and questions also. So thank you for the presentation and the manuscript. First of all, I have a remark on the manuscript that is clear in general, but there was something that was difficult to do a little bit. Is that between chapters we did not add an effort of mapping the flow of the relation. So one kind of summaries of different work and perhaps some factors that you see, okay? But we have a lot of redundancies between from one chapter to the other. When for the reader, it's not very useful and quite disappointing. But for the so also I'm not a specialist on that. So also my questions may be quite naive. I have a lot of questions, but of course I think we won't have time for all. First one is something that I've already been discussed a little bit. You have spoken of visual okay. So you realize that it's required to have a visual assessment in order to have a good estimation. This means that the brain or the eye and the brain are doing a better job than the algorithm. Okay? Yes. But the brain and is doing computation also. So, in your opinion, what are the mathematical tools or measures that are missing us? Do you have an idea?
Yes, I said partially answered the question, but visually, and the problem with because it's removing some details. That's why the already the criteria PS and the SSIN is not providing good results because of that's why we said visual. And visually is not ultimate solution to having good results. We need to employ the reconstruction as a loss function inside the network. So then it cannot, remove the details. You see the black dots, and there is some like small details is missing in the nuance results. That's why the structural similarity is not matching. So the problem is not only with the SSIMT, the problem with the results as well. So we need to improve the results. Then these existing criteria can give better results.
Okay. Maybe my remark or questions are coming to the landscape. In your first chapter 2, you have used the samples at the legal speed, and I was quite surprised for testing the different because the speed that is interesting us in your project is the fastest one, because this is the most interesting for us. So why have you choose this?
Our target was faster, but at least the first one, the medium, start from here to going to the faster.
Okay, and at the end of this chapter, it's quite funny because you say that the study of the specific features of some images, a difficult problem. If them are very specific,
Yeah.
so it's more easy to, it's easier to deal with, no?
It can be.
I don't know, it's just a question.
I mean, the same, the noise is based on the parameters. I mean, the environmental computation. It's changing. It's not predictable. So it's not straightforward, like focusing on the one distribution. It's something different. That's why we say that it's important to do analysis.
Okay. Also, in chapter 3, in table 2.1, I want to find also because say that you compare a list of different methods, and you have GB and sketching. Okay, but in the table they have the exact same results. So I was surprised that you choose sketching because for me GB is better because it's GB is included in sketching.
Yes, that's right.
So GB is more efficient.
GB is more
There are
efficient,
less
but
computation with GB followed than with the stacking.
but
But it gives the same result.
yeah, but stacking it utilizes itself is overfitting tackling procedures. So that's why I thought that stacking can be more secure. That it can reduce the error bias. It can reduce the biasness. That's why. In fact, it was known as super learner because of that.
Okay. Okay. You distinguish scan speed and doing but you can part of the meaning can speed and doing time. I don't understand why because for me it's the same thing. They measure quite the same thing.
Yes, yes.
Why
It's not only good.
Okay. So there is no it's not important. And I have a technical question. The need to know about the algorithm that means of labels of Windows. But I was surprised to use this kind of computation to detect I mean, like smooth areas because once again, I'm not to say that I found that, for example, standardization to be a big issue. I'm surprised with this.
The mean shifting is normally using the literature for identifying the small variables.
That's what is the advantage according to other standardization.
So if we find the higher shifting the mean values from maximum, the higher density results of any image can give in terms of pixel mean values, so that we can have the details of the noise information. And of course, there will be flooding, not any different pixels, because additional picture mislead them.
Also, in algorithm 2, in your version, in application version, as I'm sticking and there is an error. Because there are certain things not right. So, and that's interesting to correct it before the
Yeah, sure.
In chapter 5, I have another question concerning the data set you used in chapter 5 because you mentioned that you have used the display methods in input. It's okay. Display in chapter 5.
Yes.
But it's quite surprising for me because you are working on a denoising algorithm. And JPEG is making a lot of image processing in your input data in the
Yes.
original between them. You know, for professional photographs use raw images to have the exact input. And you use fake images.
Because those samples we found in the literature in the same format.
Yes, but it's surprising that this, okay, but this data set is not originality at the start. The objective of this standard. Okay.
No,
Because it's surprising.
It was from 10 different class, and it was using for classification.
And did you try to, did you, yes, try to think about what is the perturbation that is added by the algorithm? Because you want to know.
Yes, I didn't.
What kind of term?
Yes, because
I don't know.
normally it is used for classification of the literature.
Yeah, that's
We were not finding
but perhaps this is not the exact the right data set. So it's not over. It's not right. Well, I'm surprised because I think you see some results. Alors perhaps I do not understand the name. I think you have this on your slide. You know, it's the comparison between ResNet and this is the table with ResNet and CDU, but I'm not sure what you show. Yeah. So you have an accuracy of 0.5.
For gamma, yes.
Yeah. So the 0.5 is a random.
Yes, I said that for gamma it doesn't work.
Yes.
Yes.
It doesn't work at all. So
Yes.
Random is a
Simple neural network is a two-layer network, like Motiur. But ResNet was the pre-trained technique is performing as a feature extractor. So it has previous knowledge on other images, and from my data set, it was giving extracting features and giving these features for training.
okay. Just a small remark in chapter 6. I think if there is any question that is not correct, but we will see that. So now I will give the floor to the supervisor and I need so thank you. So the how can say is finally at the beginning the program was generated and at the end we do the data synthesis database. So this is yes something special that means probably we develop more new network that finally we develop dataset with Android and test tools. I don't know if you have a philosophy of mechanisms, but probably yes. The data is very important. One problem is grow the data set. At the beginning, we were expecting to take a lot of our data set on the SVM, and very complicated because it's noisy images, and people when they use the SVM, they don't want to know. So it's complicated. The other thing, finally, people say is dwell time. So I think dwell time is really the most important parameter in the game. What you do dwell time is also in the literature. You have a lot of publications about the dwell time, and it has a range going one and clearly noise. And also once we don't want to we want to use the sample directly without coating and scan very fastly and avoid the problem of what my colleague Olivier was saying. So, particularly when you have very fragile sample specimen, if your dwell time is high, so if the goal is really of the sample, you take it, you put, you scan fastly, and you get it. This is the doing. The problem with the physical validation, we already think about it, but it goes to more fundamental aspects, and I just know if we really have time and money for this, it's to go to Monte Carlo simulation, and then to really consider the time between the two, and then you can manage and really know what kind of noise, because for sure now I don't know the type of noise in the SCM. The literature say yes, if you have many random variable, it goes to Gaussian. So we were effectively expecting Gaussian. But we don't find have Gaussian, have Poisson, we say gamma, and finally you say speckle. So for sure, it needs a scientific point of view. There is a lot of things to do. I don't know.
In fact, the findings of gamma, it is not like we are not the first to find the gamma. We see one study performed by one researcher collaboratively with polytechnic in Paris, and mostly the working was from I forgot the university name. He was using generally the resonant network for his
Yes, but yes, between United States and Israel.
yes, no USA, it's
USA,
Paris.
Yes.
Tel Aviv University. So they introduce
But
inside
it was
no, sir.
it was not
Scanning
and you are sure? Okay, good. But anyway, I think
It was they were using gamma as a like for performance.
yes, we are. Okay. Yes. Okay, thank you very much. Now, donc, Michel Salomon, le directeur de l'équipe.
Tout à l'heure, il y a quelqu'un qui voit plus gros dans cette technique. It was what I imagine at the starting of that step. It's different because I work on the design of the new network, but this is this work the analysis of the data problem, what you want to do or what you want to know, something that you need to keep in mind in order to take the direction of that. But because we have seen also that the central there are things to already investigate and at some point that research about and it is something different so that still some things open but what to do. One Thank you.
Thank you very much. Thank you. So now we are going to get the so perhaps you go out and we stay here because of the video. Thank you.